Hello everyone. Today we will be talking about bonding. Now when an element bonds, it is the outermost shell or the electrons in the outermost shell known as valence electrons that interact. But how do we know how many valence electrons an element has? Well, let's look at Lewis dot symbols. Lewis dot symbols shows the number of valence electron for each element. But let's look at this periodic table so you guys can figure out how many valence electrons does each element has. So group 1 has 1 valence electron, group 2 has 2. Every transitional metal has 2 valence electrons. And then group 3 has 3, 4, 5, 6, 7, and 8 valence electrons in that order. So let's show this using Lewis dot symbols. Lewis dot symbols, you put the element and then you put how many electrons, valence electrons it has around the element. So sodium, because it is in group 1, it has the 1 valence electron, so we only put 1. Magnesium has 2, boron has 3, carbon 4, nitrogen 5, 6, 7, and 8 for neon. Notice how in carbon, it's 1 electron in every area around the carbon. And for nitrogen, once you actually have extras, that's when you can start pairing them. So each area around the element has to have at least 1 electron before you can start pairing. Just go back to electron configuration and it's the same thing there for when we have orbitals with the same energy. And also notice how neon has no unpaired electrons. This is the reason why they are highly stable and highly unreactive. Ionic bonds. So ionic bonds is a bond between a metal and a nonmetal, or a cation and an anion. And it's not necessarily a bond. It is an attraction between the cation, the positive charged element, and an anion, the negative charged element. Notice how the electron that's supposed to be in sodium got transferred to the fluorine. Correct? If you remember from your periodic trends, this is exactly what happens. And now that one is positive and one is negative, they have an attraction between them. The next part is about lattice energy. Lattice energy is the energy required to break an ionic bond. How do we do that? We use this formula. E equals K times the charge of the positive ion times the charge of the negative ion divided by R squared, the radius squared. Now for this equation, we don't necessarily have to find the value, which we're usually comparing two compounds and trying to find out which one has a higher lattice energy. To do this, just look at the charge of the elements or the ions in the compound. For example, if we had magnesium, it'd be a 2 because magnesium is a 2 plus. And then we multiply those. Now the higher this multiplication of the charges is, the higher the energy. Say we have two compounds with the same energy, with the same charges. Then we look at the radius. If you go back to periodic trends, the smaller the radius, or the higher in the period, in the group, the smaller the radius, the higher the energy. Covalent bonds. Now covalent bonds is the actual sharing of electrons. It is an actual bond between two elements or more. Now let's look at this chlorine. This is a Lewis dot symbol for both chlorines. Notice how it has 1 unpaired electron there and 1 unpaired electron there. So those 2 electrons will be shared between the 2 chlorines to form this type of Lewis symbol, Lewis dot symbol. Notice how now they both have no unpaired electrons. This makes both of them highly stable. How do we know how many bonds an element can have? Well, for that, we use the octet rule to find out. So the octet rule just says that every element should have about 8 valence electrons to be stable, just like a noble gas. But in reality, this only happens for carbon, nitrogen, oxygen, and fluorine. Now, exceptions. Hydrogen can only hold up to 2 valence electrons, meaning it can only make the 1 bond. This is because it only has the 1s orbital, and each orbital can only hold 2 electrons. Now boron can only make 3 covalent bonds, or can only contain 6 valence electrons. This is because if you look at the Lewis dot symbol, if you go back on the video and look at the Lewis dot symbol, boron only has 3 electrons, so it can only make 3 bonds. You need to have an electron there so you can bond. It is a sharing of electrons. So boron can only make 3 bonds. Now elements from period 3 or higher, they can have what we call an expanded octet, meaning they could have more than 8 valence electrons. And this is because from starting in the third period, the d orbitals exist. To explain this, we talk about hybridization. And hybridization is a combination of orbitals of different energy so that the new orbitals could have the same energy and more bonds could occur. Let's explain this through methane. Let's look at the electron configuration for carbon. If we do this, 1s2, 2s2, 2p2. Notice how carbon can only make these 2 bonds. Those are the only 2 unpaired electrons that it has. Therefore, it can only bond there. Yet we are saying that carbon could have 4 bonds with 4 different hydrogens. This is due because the 2s orbital and the orbitals in 2p combine to form 4 sp3 orbitals. Now sp3, because we used 1s and 3 p orbitals. And now the new electron configuration for carbon looks like this. And now if you notice, it can actually make 4 bonds. And this is what happens for carbon. And to show this, we use the Lewis structures. Notice how now carbon has 8 electrons around, so it is highly stable. And hydrogen follows its rule of only having 2. Now instead of just putting the dots, we represent the bonds by drawing a line between the 2 elements. And this is the correct Lewis structure for methane. Now let's look at something that has an expanded octet, like phosphorus. So this will be the electron configuration for phosphorus. And the reason why we have the 3d orbitals, it's because we are at the 3rd energy level, and d orbitals exist starting at the 3rd energy level. Based on this electron configuration, we see that phosphorus can only make 3 bonds. Yet we have compounds such as PCl5. To explain this, we say that 5 orbitals are going to hybridize. And those 5 orbitals are the 1 3s, the 3 3p orbitals, and 1 from the d orbitals to make sp3d orbitals. And now the new configuration looks like this. 1s2, 2s2, 2p6. And if you notice here, now that those energy levels have hybridized, those orbitals have hybridized, you can have 5 bonds. Let's look at the Lewis structure for that. Notice how phosphorus now has 10 electrons instead of the 8. This is highly stable for phosphorus because it could have the expanded octet. And then same thing as before, we just do the line where they are sharing electrons to show how they bond. Now this is it for this video. For the rest about bonding, look at the next video. We will talk about formal charges and resonance structures. Thanks for watching.